In section 5, we're going to continue our work on exponents and radicals. Now you recall from an earlier lesson when we said if we were going to multiply variables with exponents, if the bases were the same, a shortcut to it is you just add the exponents. So we had done that earlier. But now we're going to take a look at when we are going to divide. Now, keep in mind, this would be 6, or I should say 5 factors of 6 on the top, 2 factors of 6 on the bottom, and some of these would cancel out. And we would be left with 3 6s on the top, which is 6 to the third. So if when we multiplied variables with exponents, we added the exponents, what do you think would be a shortcut here to get the same results? Multiplying, we add. So subtracting, bring our exponent 2 up from the denominator, crosses this division bar, and the sign of the exponent changes, and we get 6 to the third. And that's the basic rule. And there's the rule in its official form. Now let's take a look at example 1. And in a sense, this is something basically easy. We're just going to subtract exponents when we divide. So the 4 comes up, becomes a negative 4, 5 to the third. The 5 comes up, becomes a negative 5, and then again our base is what's in the parentheses to the 5th power. The same thing here. Now we're just doing the dividing, we're not expanding what's here. We've done that before. Now we ended up with something like this up there, and I said this wasn't complete. We're now going to take a look at the power, the product of a power to a power. Now both of these have an exponent 1 that we don't write. And what this is saying is we have this written 3 times. And what they're saying here is we're going to take that 3, that exponent 3, and multiply it by this 1. So this gives us 3 to the third and c to the third. And that's what they're illustrating in this rule. Okay? Now, keep in mind, and they're showing us this example here, 2x to the 5th. Sometimes people will write it 2x to the 5th like so. Well, that's not correct, because you also have to raise the 2, which is to the 1st power, to the 5th power. That's a common error, and I'm glad they pointed it out there. Now, the quotient to a power rule is when you have a fraction. Remember, there's a 1 exponent by each of these, so that the exponent on the outside of the parentheses applies to each part of the fraction. And if I were taking notes, again, I'd be sure to include something like this in my notes. Okay, let's take a look at example 2 now. Now again, there's a 1 by each of these, an exponent. So this becomes 5 to the third, y to the third, and we simplify. 5 to the third is 125. Now here we're going to multiply each of these variables and their exponents by 4. So 2 times 4 is 8. 3 times 4 is 12. They're showing you just the intermediate step here. Normally you would go directly to this one. So here in the numerator, x to the 6th, and then 2 to the 6th is 64. A to the 4th raised to the 3rd, that would be 4 times 3 is 12. 3 times 3 is 9. So as long as you remember the difference between these two rules, a to the 2nd times a to the 3rd, and then a to the 2nd raised to the 3rd power. Here we're just adding our exponents, a to the 5th. Here we're raising this to a power. This will be a to the 6th. And students get this confused. They're not sure when to multiply. You multiply in this situation. And for letter E, let me take you through it step by step. So the first step would be get rid of these innermost parentheses. R to the 3rd, S to the 3rd, over R to the 4th. Now, what I would do here is I would actually do some simplification here. This R to the 3rd, R to the 4th, we could take this 3, subtract it from the 4, and this would end up being a 1. So let me do that. This is going to disappear completely up here, and this ends up like so. So now we're going to raise it to the 2nd power, s to the 6th over r to the 2nd. Okay? Now, interestingly, the book is also showing us that if we didn't do this simplification at this step, and we did it out the long way, the answers come out the same. It's just a little easier to do it this way. We're going to take a look now at negative exponents. So suppose we have this condition right here. Again, this would be like a over a times a. And here, the a's would cancel out, and the 1 that would appear before the a, which we don't usually write, would remain there. And this would be 1 over a. 1 over a. Now, if we use the rule we had, where we take this exponent, cross the division bar, it comes up here as a negative 2. We're left with a to the negative 1. Well, we just proved that a to the negative 1 is actually 1 over a. That is, when you have a negative exponent in the numerator, by dropping it down to the denominator, it becomes a positive exponent down there. And we'll see some practice, and this is the rule officially. So, going over these examples, remember every number is over 1, and there's a 1 in front of every number. So if we take our base and the exponent down to the denominator, as it crosses this division line, the exponent changes its sign, and we simplify. and we get this. This is very similar to the one we've just done. And again, as this comes down, it changes its sign, and we don't write the exponent 1 as a rule. Now, for this one, I'll show you a shortcut. Here we have 3 over 4 to the negative 1 power. Well, here they're showing it out in detail. The shortcut is, whenever you have a fraction that's to a negative exponent, the simplified rule is just take what is in the parenthesis, flip it, that is, use the reciprocal, and the exponent now becomes a positive. So in a sense, to the first power, it's just 4/3. And for this one, I guess I went a different pattern. Again, there's a 1 there, and this is over 1. We just bring the base and its exponent across the division bar. The 1 stays in the numerator, and the exponent becomes positive. And to simplify this, 5 to the 4th is 6/25. Sometimes students will forget and just put 6/25 and not put it as a denominator. Remember, when it's a negative exponent in the numerator, this will end up in the denominator, and you must show it that way. Now for letter D, let me write that out. Negative 4 to the negative 2 power. Now remember, there's sort of like a negative 1 there times 4. And that's over 1. So what is your base here? What is your base? Is it negative 4 or just the 4? And the answer is just the 4. So the 4 then, with its negative 2, goes down to the denominator as a positive 2 exponent. But we're still left now with the negative 1 up there. And again, we said the best place to put that negative is in front of the division bar there. And then we simplify 4 squared and get 16. So our answer is a negative 1/16. And now the textbook is giving us a little more information about that shortcut. When you have a fraction that is to a negative exponent, just by flipping the fraction, taking its reciprocal, the exponent becomes positive. So here they're summarizing this little rule. This is called the inversion property. And as we look at examples, we can check these out here. 2 over 5 to the negative 3 becomes 5 over 2 to the 3rd. We expand the exponent, 5 to the 3rd, 2 to the 3rd becomes this. And again, if we have a fraction to a negative power, we take the reciprocal, we flip it, the exponent then becomes 5, and we can expand it in this form. And of course you'll have your practice to do as well. Alright, we're now going to take a look at what are called roots and rational exponents. When we think of rational exponents, we're thinking of fractional exponents. Exponents, instead of being a whole number, are fractions. Let me give you an example of a relationship between exponential notation, and in particular fractional exponents notation, and radicals. They're really related quite closely. So here we have a fractional exponent. Here we have the radical sign. Now, what's the connection? Well, when something is in the fractional exponential form, there's going to be a denominator and a numerator to that fraction. Well, the connection between these two is that denominator, the bottom part of that exponent, actually, when we convert it to radical notation, this base, well, the denominator of that fraction actually goes in that little notch of the radical sign. And the numerator is going to be the exponent of, in this case, was our base, but now under the radical sign becomes what we call the radicand. So let's look at another one, a little different than that. This will be a to the 2/3 power. So again, we have our radical sign. The denominator of our fractional exponent goes in this little notch of the radical sign, and the numerator becomes the exponent of our radicand. Right now in this form it's the base. The base goes under the radical sign and takes along, in a sense, the numerator as an exponent. So another one. Well, let's go on to some examples. This is the one they're illustrating over here. If we take a to the 1/2 power, raise it through the power rule to the second power, this just becomes a to the 2/2, which is going to be a to the first, or just plain a. Now we said that the a to the 1/2 power was the square root of a times the square root of a is equal to the square root of a squared. And the square root of a squared is a. So you see there's a lot of relationship between, well, these are equivalent, fractional exponents and the radical expression. Now let's go to see some examples. Now they're not showing us this way I was illustrating exactly, but the 36 to the 1/2 power is the square root of 36, and that we know is 6. 100, the square root of 100 is 10. Now this is the negative square root of 225, so we know the sign will be negative, and that is square root of 225 is 15. Now here we have the 4th root of 625, which is 5. So another way of looking at these, and a little later these we'll be using this technique more frequently, but in this one it's the 4th root of a negative 1296. Now when we look at fractional exponents whose denominator is an even number. That is, in this case, the fourth root of something. There are no ways to multiply something 4 times that are all negative. Multiplying 4 negatives will give you a positive. Negative times negative is a positive. Positive times negative is a negative. Negative times negative is a positive. So that's why they're saying when you have an even number as a denominator of your fractional exponents, that is not a real number. Now, because of this being in a parenthesis, that is our base. But now with the negative on the outside, this one becomes the negative outside of the radical sign. Okay? So this one, when it's positive underneath there, because that is what our base is, this would equal a negative 6. 6 to the 4th power is this, and then they're looking for a negative value of that. Now, if you have under the radical sign a negative 27, and the number in the notch here, and by the way, this is called the index number, is a 3. That's okay, because a negative 3 times a negative 3 times a negative 3 is a negative 27. So this simplified would be a negative 3. And again, this one will be because the base is just the 32, it's the 5th root of 32 with a negative sign in front. 5th root of 32 is 2, then we apply the negative sign, and that's what they get. Now again, they're not bringing in the radicals at this stage, it seems, but that is something we will be doing, and I think a useful tool. So in looking at the rule they're illustrating here, fractional exponents can be converted to this form, where we then take our n value, that becomes our index number of our base, which is now the radicand, that we're going to raise to the value of our numerator outside. So this is in essence what they're showing you, and I'm tying this in actually to a future lesson too, and hopefully useful. So the 3rd root of 27 is 3. 3 squared is 9. The 5th root of 32, taking our index number 5, raising it to the 2nd power. So the 5th root of 32 is 2. 2 to the 2nd power is 4. And the 3rd root of 64 raised to the 4th power. The 3rd root of 64 is 4. So 4 to the 4th power will be 256. And then here it's the square root, because when we have a index number of 2, we don't write the 2 there. We assume it's there when there's no number there. And this is 25 raised to the third power. The square root of 25 is 5. 5 to the third power is 125. So again, another way of looking at this, and I don't like the way they write these fractions here, fractional exponents, but that's the way they have done it. So conveniently, in the textbook, they give us a summation of all the rules of exponents. So whether you'd want to have that in your notes or something to study, and again, you're not allowed to use it on a test, but through practice and repetition, hopefully it will become familiar to you. So here's a mixed practice, so to speak. Let's follow it item by item. So exponent -4, positive exponent 6, bases are the same. We're just going to add our exponents. We get 7 to the second, which is 49. Okay. Now here we have numbers, a 5 and a 2. When we multiply that together, we get the 10. Then we're going to have x to the 2/3, x to the 1/4. Well, in order to add those together, I have to have a common denominator. In this case, it's going to be 12. And I'm going to use the technique of making each of these fractions equivalent fractions having a denominator of 12. So I've got to multiply this by 1 in the form of 4/4. And I'm going to multiply this one by 3/3. That's the one I'm going to multiply this by. So our denominators become 12, and our numerators now become 8 plus 3 is 11/12. So we have the number 10, and then x to the 11/12. Again, I don't like the way they write that, but I've said that. So here we're going to bring our -6 across the division bar. It now becomes a +6. And this gives us 9 to the 20th power. And I'll clear this up. Now for this one we have, let me write it out here. So I've just rewritten this in a form I like better. But notice as we bring this fraction up to the numerator, we have to have common denominators to work with this. So I'm going to take that 5 and I'm going to make that into a fraction with a denominator of 3. See if you know what I'm going to put there. How about 15/3? Is that another way to write 5? Yes, I'm multiplying 5 by 3/3 and getting this. So now when I bring up my denominator exponent, it's minus 4/3. And I now have, and the 2 stays below there, but this is going to be c to the 11/3. And there we have it. And there's my answer. Now when you write your fractions, because of MathLab, remember this bar will always be horizontal, not that diagonal line there. Example E looks a little challenging, but our bases are the same and our denominators are the same. So this is just going to become 6/3 when we add it, which is actually 6/3, which is actually a 2. So all of this on top, after we do this multiplication, becomes a 2. And to keep our exponents positive, and remember this is times 1, we're going to bring our 2 down, subtract it from the 3, and we get 27 to the first. So there's our final answer. Again, it looks a little challenging, but not that bad. Now again, the way they've written it, it's a little hard to work, but I've written it again the way I like. So this is going to be 2, and when we multiply negative times negative, it becomes a positive 12 sevenths. So it's just a little hard to understand the way they've written it there. But there's our answer. So looking at example B, I've rewritten it. Now notice we can square the 3, that's going to become a 9. And this part, when we simplify it, 2 goes into there once, 2 goes into there 3 times, so we just get 5/3. And then here, 2 goes into there once, 2 goes into there twice, we get y to the 3/2. So they went through a number of steps. We did ours all in one, or sort of. I did separate my numerator and denominator here. Okay, let's take a look at C. Perhaps if you see it written this way, why it's so much easier than the way they're showing. Here we're just going to add these now. As we multiply through, we get, which is adding exponents, m to the 9/3 plus 2m to the 3/3. Here this gives us m to the 3rd plus 2m. And again, they made it a little more complicated, but hopefully you can see what we've done. In example 9, letter A, this will be m to the -6 over m to the 4th. Now remember there's a 1 there. We just will bring down the -6, add it to the 4. This becomes 1 over m to the 10th. Example B, I've written it out. The 6 times 2, we just multiply and get 12. Our bases are the same, so we have to add our exponents. We have to make them equivalent fractions. So I'll multiply this one by 1 in the form of 2 over 2, and this one by 1 in the form of 3 over 3. My common denominator is 6, so I get 4 minus 3 here, which is 1/6. Now I've written out item C here, and the first thing we would do is separate this into 2 parts. Put a little dot there to indicate multiplication. So what I have left on the top here is x to the 1/2. I'm now going to take this, because of its negative exponent, and remember there's a 1 down there, bring this down, when it goes down to the denominator, this -3 becomes a +3, and this becomes 4. And that's our answer. Again, they show it in much more detail, but basically the key is separate this, then bring this negative exponent down to the denominator, and you get this. Now the last one is sort of interesting. They want us to write a to the negative 1 plus b to the negative 1 as a simplified quotient. Well, this is actually 1 over a plus 1 over b, and now we want to add these. Well, what's our common denominator here? Well, it's ab. And what do I need to multiply this by to make this denominator ab? Well, I'm going to multiply it by 1 in the form of b over b. And to make this ab, I'm going to multiply it by 1 in the form of a over a. So I now get b plus a over ab. Now I could have written a plus b, but this is fine, and that is our answer. For example 10, now we are seeing that the total number of students in millions attending institutes of higher education can be approximated by this function, where 10 corresponds to the year 1990. Find the approximate number of students in higher education enrolled in 2012. Well, how many years is that from 2090? Well, it's 22 years. And x we know is equal to 10. So we have to add our 10 to the 22. And we get 32 then for our x value that corresponds to 2012. We put 32 where the x is. Remember, we must raise it to this power, and we use our calculator for that by putting 32 caret 0.357, get a value for that, then multiply it by 5.8, and we get the 20 million students. Okay? Here they're telling you that your value of x is greater or equal to 10, and then we have 22 years more from 1990 to 2012. Again, that's where we get our 32. Now, I anticipated this earlier in the lesson, and I see here's where they're introducing it, and that is a fractional exponent is equivalent. We put our denominator as our index number, our base becomes the radicand, and our numerator is the exponent. And that's what they're showing. So, some of these now should be easy since we've been using this. The fourth root of 16 is 16 to the 1/4 power is 2. This is a negative 32 to the 1/5 power. We did that one too, and that's negative 2. And we can just see these now. Nice. We have been vindicated. Okay. They're continuing to give us detail of what we already mentioned, so fortunately I think we can pass through that. Now remember, they said as we look at our index number, if our index number is even, then we are not allowed to have a negative value as our radicand. That's not a real number. But if our index number is odd, it is okay to have a radicand that is negative. This is a rather long lesson. Let's see if we can wind it up here. So if we have our index numbers are the same, we can just multiply our radicands, and we get this. And if this is a perfect square, which it is, we can simplify it to that. And here we can separate our radicand into two radicals. This becomes the square root of 7, but now we see the square root of 64 is 8. So we're simplifying these expressions. Now in letter C, as you look at it, we're subtracting, but yet we're wondering what we can do. Well, the square root of 75 is actually the square root of 25 times the square root of 3, which is 5, the square root of 3. And the square root of 12 is actually the square root of 4 times the square root of 3. And the square root of 4 is 2, the square root of 3. We are simplifying by taking a value like 75 and putting two sets of radical signs, and under one we are putting the largest perfect square we can get out of there, square factor, and then doing this to result in 5, the square root of 3. Now, when we are simplifying expressions like this, if our radicals are the same, we just deal with the coefficient of these radicals. 5 minus 2 would be 3, the square root of 3. And that's what they're showing. In example 13, they're asking us to FOIL this. So as we FOIL our first, we get the square root of 16, which is 4. As we multiply our outers, we get a negative 5, the square root of 2. As we do our inners, we get plus 3, the square root of 8. And as we do our last, we get a negative 15. Now, let's take a look at 3, the square root of 8. 3, the square root of 4, times the square root of 2. We're using that simplification process. The square root of 4 is 2. So 2 times 3 is 6. So this is going to become 6, the square root of 2, after I simplify that. That's sort of the magic of video here. And we have a plus there, okay. So now we have a 4 and a negative 15, which will give us a negative 11. And we have a negative 5 and a positive 6, which will give us a 1, the square root of 2, and we don't write the 1 usually in front. And that is right there. Now in example B, we're seeing an interesting arrangement of terms here, that these are the same in both, except one is negative and one is positive. Well, these are actually what we call radical conjugates. This is a U here, okay. Now, we're going to use this tool shortly, but what happened when we multiplied conjugates from an earlier lesson here? Well, it ended up as being a squared minus b squared. That is the difference of squares. Well, if we're dealing with radicals, a similar thing happens. This, when we do our first, becomes the square root of 49, which is 7, minus, and this becomes the square root of 100, which is 10. So we end up with a negative 3. So this tool is going to be added to our toolkit here shortly. So in example A, we're asked to rationalize the denominator. Right now, the square root of negative 3 is irrational. So what can we multiply it by? Well, we can multiply this fraction by a 1 in the form of the square root of 3 over the square root of 3. Now notice, by doing this, this becomes the square root of 9, which is 3, and this becomes 4, the square root of 3, as our numerator. Now for letter B, we're going to use our tool, which is multiplying this by 1, but the one that we're going to choose is the conjugate of this. So it'll be 3 plus the square root of 2. 3 plus the square root of 2. So when we do that, our numerator becomes 3 plus the square root of 2, and we FOIL our bottom. 3 times 3 is 9, minus the square root of 2 times the square root of 2 is the square root of 4. Square root of 4 is 2, so 9 minus 2, which then gives us 3, the square root of 2, over 7. We have used that radical conjugate to rationalize our denominator. And now for our last example. So here they want us to rationalize the numerator now, not the denominator. So we're going to use the radical conjugate of the numerator, which I've set up here. So my numerator, I guess I can put it over here, becomes 2 minus 5. So my numerator will eventually become a negative 3. Looking for a place to put it here. A negative 3. Now my denominator, as I FOIL, is 1 times 2 is 2. My outer is a negative square root of 5. My inner's plus 2. The square root of 3. And my last, a negative square root of 15. Now I've rationalized the numerator, but my denominator certainly looks amiss. And that's it. So again, be careful when they ask you what to rationalize. And you'll have practice, and good luck with your practice and quiz me on this.